Okay, so welcome to this lecture session on engineering mechanics. This will hopefully guide you through all the initial topics that you have for the first CT. So of course we have force as a system of vectors, Lami's equation, equilibrium and friction. So let's start with vectors, and vectors is something we all know and are very familiar about, but there are some things that you don't know, that is force in 3D. So let's say we have some force F which is acting along all three directions of Fx, Fy and Fz. So we can represent this as vector additions, and as a result of this we can write magnitude of f as fx square plus fy square plus fz square, and this should be also square. So considering this, therefore we can write down fx by f square plus fy by f square plus fz by f square is equal to 1. And therefore we can say that cos theta x plus cos theta y plus cos theta z is 1. Squared of course, is equal to 1. So basically the angle theta here represents the angle that the force makes, the resultant force makes with its components along the x, y and z axis. And therefore we get this equation. This is something that you must have learned in 3D geometry in your earlier classes. So that is all there is to vectors, and this is something we will need when we solve sums of 3D. Now let's come to our next topic, which is the first basic theoretical topic, that is Lami's theorem. And according to Lami's theorem, first basic, let's say, limitation of the theorem is that you can only apply it to up to 3 forces, not up to exactly 3 forces. And I'll show you how you can use more forces and also apply Lami's theorem. So first let's see what the basic theorem says. Let's say we have 3 forces like this, P, Q and R. This is angle alpha, this is angle beta, and this is angle gamma. We can write P by sine alpha is equal to Q by sine beta is equal to R by sine gamma, and this is basically what Lami's theorem says. So where can we apply this? Let's say we have a block and we have 2 walls like this, and the block is connected something like this. So this is a wire and this is a wire. This is perpendicular. This is suppose A, B, C, and this block weighs suppose 100 Newton. This angle is 37 degree. Now you're asked to find the forces along A and B. Now there are 2 ways to solve the sum. The first thing is resolve into components, and then since the body is at equilibrium, something that we will talk about a bit later, we can simply do summation of fx is 0 and summation of fy is 0. So from here you can see that this force A is along fx, this force B will have a component bx, so we can write A plus bx is equal to 0 if we take appropriate directions, and this force B has a component by, and this force is entirely along y-axis, so we can write by plus 100 newtons is equal to 0. Now of course this will be negative, let's say, and this will be negative. So we basically A is equal to bx and by will be is equal to 100 Newton, and from that you can get the solution very easily. However, if you're asked to specifically use Lami's theorem, and in many cases Lami's theorem will be the easier way to solve sums like this, what we will do is we will simply draw the diagram of the forces. So this is my A, this is sum B, and this is my 100 Newton. I know this is angle 90 degree. Now I need to check this angle. So if this is 37 degree, this is pi by 2 minus 37. So basically 90 minus 37, and we know this is also 90. So that will be pi by 2 plus pi by 2 minus 37. So that will be pi minus 37, or we can write this as 180 minus 37 degrees, and then you can simply calculate this angle. So this angle is of course 37 degree. So this is also pi by 2. So this angle in general will be 90 plus 37. And from here you can write A by, so this is the force A. Now you need to take the angle which is opposite to the force. So this angle. So A by sine 90 plus 37 will be equal to B by the angle opposite to B. So this one, sine 90, is equal to, of course, the 100 newtons by the angle opposite to it. By this time you must have gotten it, 180 minus 37. And there you can solve the entire system in a single equation. Lamè's theorem can also be applied to more than 3 forces, and the easiest way to do this, let's say I have forces like this. This is A, B, C and D. So of course you know that we can take these two forces and calculate their resultant force. The magnitude of resultant we can of course find out by root over c square plus d square plus 2cd cos 60, cos theta, not 60, whatever the angle is. And this plus sign or minus sign will change according to the direction, or you can just take the appropriate value of theta and you can get that in that way. And you can calculate the angle of r theta, and using that you can combine these two forces into some resultant forces r and solve it that way. Or of course you can also break C and D into x and y components, merge them together into a resultant force and use it that way. We usually use this when we are calculating, let's say, a resultant normal force. So that's all about Lamè's theorem. It's a rather easy portion and question should be rather simple. The next thing we talk about is of course equilibrium. Now before heading into equilibrium, we need to understand another thing, that is moment of a force. So what is moment? If I need to express it in layman's term, I will say that it is the force that starts a rotation. Now of course this is no definition, but this is just a layman's term of explaining what moment of a force is. So of course if I have, let's say, a force, this is suppose the r vector and this is suppose the f vector, and this is the point A. So if I need to calculate moment about A, I will write this as r cross f. And you can understand that since this is a cross product, this is also a vector. Now what is this implying? That if let's say this were a body of some sort, then this force will be producing this much torque about the point A, or that means it will ask the body or make the body rotate with this much force about A. So with that being said, let's understand this a bit better, and the easiest way to do that is tackle questions. So I will be taking up a question from Madam Craig here. So let's say we have a pole centered over here at point O, and we have some sort of a lever like this. About the lever we are applying a 600 Newton force. This is point A, this is point O, okay, I have already marked, and this height is 4 meters. This length is 2 meters. This angle is given to be 40 degrees, and you are asked to find out the moment about base O, moment of 600 Newton about O. Okay, so first there are actually a lot of ways in which this solution can be achieved, right? So the first thing that I can do, or the rather simplest thing I can do, is, let's say I connect this straight. Okay, I imagine like there's a scale which connects the point A to the point O, and this length is D. Now, so from geometry, I can see that D is equal to 4 cos 60 plus 2 sin 40. This is of course using simple trigonometry. You can just see it on your own. You can solve this and you will see that this comes out to be about 4.35 meters. So by using these two lengths and using these two angles, which I know, I've calculated the value of D. And by M is equal to FD, what I can say is, okay, by the way, wait 1 second. I did one basic mistake. I took this D perpendicular to the force. Okay, so this might not join at A. Okay, I just took it so that it's perpendicular to my force, and I calculated D accordingly. Okay, so with that I got to the value of D, and since this length D is already perpendicular to my force, I can simply use moment is equal to F of D. So I can write down is equal to 600 into 4.35, which is equal to 2610 Newton meter. I would ask you to verify this result on your own by solving it in a different way or by some other way which you can imagine. Okay, now this is one way of solving it. Can we think of it in some different way? The answer is yes. We can think of it by, let's say, resolving the components, right? So let's take this force. Let me quickly erase whatever I have done here. Now let's say I split this force into components. This is, suppose, F1 is equal to 600 cos 40, and this will be F2 is equal to 600 sin 40. And now I can say that F1, if you put into calculator, will come out to be 460 Newton, and F2 will come out to be 386 Newton, right? Now if you see that the perpendicular distance from O of F2 is this 2 meter, and the perpendicular distance of F1 from O is this 4 meter. So what I can write the moment as is simply F1 into my 4 meters and F2 into 2 meters. And if you calculate this, this will be 460 into 4 plus 386 into 2, which will give you 2610 Newton meter, or the same and the correct answer. Now, even though this looks very simple, this method actually uses a theorem which lies hidden. The theorem is known as Varignon's theorem, which states that total moment about a point will be simply equal to algebraic sum of all moments. This will also be useful for solving equilibrium problems. Basically, what we did here is that break the force into its components, then treat each of the components as a different force, and simply did an algebraic sum of the moments of those components, and hence we got the net moment, which was correct. Now we can also use the principle of transmissibility, and this is a little bit more complex, and I'll still try my best to explain this. Basically what you can do is, see, this force is acting along this direction, right? So what we can do is, let's say I somehow select this force. Okay, selected more than I wanted to, just a sec, and I move it along its direction so that it comes into contact with this rod's imaginary extension. Now, what the principle of transmissibility says is that something you have already learned in vectors in your previous classes is that if we keep the direction of a vector with the axis constant, we can move it to any place and the vector will not change. So as long as the magnitude and the direction of the vector is constant, you can change your point of reference or where the vector lies in space, and that will not affect its direction. So the simplest example which you might have learned is that if you have two vectors like this, you must have shifted this vector to over here, something like this, and then calculated the resultant using the triangle law like this. In the same way, you can shift this force to over here and then calculate the moment if you can calculate this distance. And of course, we can calculate this distance by simply saying that this distance, let's say this net distance, if I consider to be d, then I can simply say that d will be is equal to our original 4 plus 2 tan of 40. This will give you 5.68 meters. So now we have this entire distance from O. And from that, what we can say is m0 will be is equal to 460 into 5.68 or 2610 Newton meter. Since the point lies directly above O, we can calculate the moment in that way. Now, what we can also do, so this is shifting the force upwards and doing it. What you can also do is shift the force downwards. So instead of taking it to O, what you can do is you can take it downwards to, let's say, a point C. So one thing I forgot to explain here is that I took 460 because the vertical components, of course, will not apply any torque. I need to take only the horizontal components. So if you remember, this came out to be 460. This is what we took. So in the same way, what we can do is we can select this force and we can simply shift it along its original point to the base. And in this way, what will happen is the horizontal component will get cancelled out since it is in the direction of the perpendicular, and we know that sine theta will be 0 and that will simply get cancelled out. So what we'll be left with is only the vertical component. So once again, you will need to form a triangle, calculate this distance. So this you know already is 2. This distance you need to calculate and you will get the answer. So earlier we did the vertical distance, let's say d1. Now let's see the modified horizontal distance will be 2 plus 4 cot 40 is equal to 6.77 meters, and we will get the force, basically this distance 6.77 multiplied by, we will need the vertical component. Once again, remember, only the force component which is perpendicular to the r vector will apply a torque. Any component which is parallel to the r vector will not apply any torque because it cannot rotate the body. So once again, we can calculate this. So value of F2, if I go back, F2 we had calculated to be 386, and this will also give you 2610 Newton meters. So I hope I have been able to explain the implications and the applications of moment of a force and how you can easily calculate the moment using all of the basic principles that you have in mechanics. So with that being done, we have done moment of a force. So we are cool to move on to the next part, which is equilibrium. Now, equilibrium can be thought of as two ways. The first is equilibrium of motion, and that can either be in 1 dimension or 2 dimensions. And the second, also it can be in 3 dimensions, but I am yet to see any questions from that. And the second is equilibrium of rotation. So in general questions that you might get, you might be given to solve either this, or you might be given to solve this, and you might also be given to solve a combination of both of this, and we will see how that is applied. So the easiest way to actually go into equilibrium is to basically learn questions. And the way I will be doing it is merging it into another topic which is in the syllabus, which is known as wedges. So of course, wedges is just a slant surface. This is a wedge, right? And this is slant at some angle, suppose alpha. As simple as that. So let's take a particular scenario. Suppose I have a big, huge block which is slant something like this. 1 second, let me. Okay. And it is placed on, let's say, a conveyor belt which has bearings, something like this. Okay. This is of mass m. Now you have a wedge below the block. So let me just extend the wedge so that it is clear. Something like this, which has an angle alpha. A force P is applied for the wedge to stay in place, and this wedge lies on a ground like so. Now it is given that the coefficient of friction mu is equal to tan some angle phi. This is something which you are expected to know from class 12. So let's talk about some basic applications of what this might mean. So if we, let's say, a body M exists on a surface like so, and it has normal reaction N. Now if you apply some force P, let's say, the force of friction will apply along this direction. Sorry, this is not normal, this is mass, let's say. Friction force will apply along this direction. Now, if you consider the normal reaction force, which will be along this direction, the resultant reaction force will be along this, and this angle will basically be phi. So in this sense, remember this concept, and we will be using this concept to solve this reaction. The P here is just sufficient so that the block doesn't move. So using that, we will find out the following concepts. So let's first introduce into another thing. So you can see how we are transitioning from one topic to another without going into details, so that everything merges together and appears at one block of chain of what you need to learn. So let's talk about free body diagrams. Free body diagrams have two basic conditions. The first condition, it should consider only one body and nothing else. And the second condition, it needs all forces on the said body. Now let's take this block. So first, it has a weight mg. It will have a reaction force from the wall R3. Now you might say there must be another reaction force here, but if you take a look at the diagram, the block wants to slide down the wedge, something like this. So it does not make sense to have reaction force against this wall. This reaction will of course be 0. Right? Now from the concept which I talked about, so I'll just draw mg over here so that I can explain the concept. If I draw a line like this, right, which is, okay, not like this, which is perpendicular to the surface, then I would have said that the reaction force is along this line from the wedge. So the reaction force, or not the reaction force, but the normal force, right? And by using my concept of friction that I just talked about, and since I know that the system is at rest, what I can say is that the actual reaction force applied by the wedge will be along this direction, R2, at an angle phi, which is the angle of friction. So I want you to go through this concept once again, because it is very crucial in understanding how friction works and making sums way easier than they actually look to be, right? So basically what this R2 tells, this R2 is the normal force plus the friction force, and that is applied along this direction. By merging the normal and friction force, we are making the sum way easier. And if you see, we have R2, R3 and M. So total of 3 forces which you can easily solve using Lami's theorem. And that's what I was talking about, remember, when I was talking about force systems in Lami's theorem. Now let's go to the wedge. So this is the wedge, let's say. Okay. The diagrams may be different. Don't worry about the diagrams too much. So this is alpha. Now, if this R2 was at an angle phi to the normal, then we can consider the reaction force like this also at an angle phi. And in the same way, if this is R2, this block will have some normal force from the ground which is perpendicular. But since this surface also has friction, we can take R1 also at the same angle phi, which is the angle of friction. So you can see how easily we are solving questions. And we know that there's a force P over here. So using this simple concept, a sum which might have taken you a long time by splitting into components and solving, we are able to apply Lami's theorem and solve in, let's say, 2-3 minutes. And with that, we have successfully created the free body diagrams of the wedge and the block, and now you can easily solve them, right? So if I were to apply Lami's theorem on this block, I can say that R3 is applied like this, then we have mg over here, and some R2 which is applied like this. This is perpendicular, and this I can solve like P is applied something like this. Sorry, P's direction is wrong here. P is applied like this, right? We have some, what else was there? R1 is applied something like this, and R2 is applied something like this. And you can solve the questions very easily like that. You can also use triangular law, and that will be basically same thing. Okay, now this question is easy here because it is, the system is at equilibrium. So we know that the angle of friction is phi. Now, what if the system was slipping? Can you think when the system will start to slip? So the first thing is, it can slip at 2 points. So either it can slip at this point, or it can slip at this point, or it can slip at both the points simultaneously. So either the blocks of the wedge itself slips like this, or the block slips downwards. So the block will slip downwards like this, right? So with that being said, can you think about the conditions when it will happen? Let's say the upper surface is slipping. This means that this reaction force, which was earlier at an angle phi, has now decreased. So this force we can still consider is at angle phi, but this reaction force has changed from phi minus alpha, let's say some value, right? Then if let's say the lower block was slipping, so the lower block face was starting to slip, then this angle has changed to some angle, let's say alpha, and this remains at some phi. So these are the two conditions. This is not very important, but keep this, that as long as R1 is equal to R2, the blocks will remain at equilibrium. But R1 and R2 can swing from 2 phi minus alpha, and accordingly you need to determine the slip at the surfaces. Okay, so if R2 changes, R2 becomes greater, it means that the lower surface has slipped, and if R1 becomes greater, it means that the upper surface has slipped. Of course, this is for this specific problem, and you need to understand your question accordingly and solve and understand the slipping. Okay, so that was really deep into moment, Lami's theorem, and wedges. So we have covered almost all of the topics which are related. We have also solved the question of equilibrium, that how we can apply equilibrium. Now there's another concept related to equilibrium, which is moment. However, I think I have shown you enough examples of solving moment that you can solve them. Just keep this in mind, that this theorem which I talked about is the utmost importance in terms of equilibrium. I will give you one example before we move on, and that example is basically like this. So we have a ball along a block like this. We have a radius of 12 centimeter, right? And this has 6 centimeter. A force P is applied like this. The weight of this ball is given to be 100 Newton. What is the max value of P such that the ball remains in contact with the ground? Now, this sum is a question of equilibrium, where the forces are balanced. So let's start by drawing the free body diagram. Let's take mg, right? We can take a normal reaction force here. We can take P somewhere over here. So this is the moment of P, and we can solve. This is completely wrong. And the reason is engineering mechanics tricks you into thinking in ways which a normal physicist can't. So if you think about what is happening, if this P is applying enough force so that the body is just in equilibrium, then this point will basically not even be applying any normal force. So even the slightest d, let's say dp is equal to tends to 0 will be enough for the ball to roll over the wedge. This means that there is no normal force from the ground, and this is a very important concept in solving questions like this. There's one more question similar to this which we will see, but let's first solve this. So what you can do is, of course, you can take, let's say this point is E. Okay, we know this height is 6, this height is 12, right? So we can simply join this like this. This is also 12, so this is 6, this height is also 6. We can calculate this value. So we can take sigma moment about A is equal to 0. Now here's something to consider. Why am I doing this? Take a look at why I should consider the point A. So if I were to draw the free body diagram, so this is incorrect clearly. Let's erase this off. And let's say I draw the correct free body diagram of this ball. So this is the point A. I do have some force mg, and I do have some moment about, sorry, not moment, but some reaction force A and a force P. Now this NA is rather difficult for me to calculate, right? I will need to solve multiple equations. Now if I take my point to be over here, so write here, then what I can do is I can practically eliminate whatever my normal reaction force was about this point A. So these will get eliminated from the concept of moments. So by making the summation of moments across A to be 0, we are basically eliminating the normal about A. And with that, what we can do is ET. So let's first calculate. Let's take this angle as theta. So we will get sine theta as 6 by 12. So theta is of course 30 degree. And what we can do is 18 into P. So of course moment about A. So this will be, this length is 6, this length is 12. So moment of P is 18 into P, and P is already perpendicular, is equal to weight of the body into 12 cos theta. So this radius is 12 and the moment will be along the perpendicular. So this, remember, weight is acting like this, right? So there is no normal force, but the weight still exists, right? So weight is like this. This is your perpendicular distance, which is r vector, and this length you know is 12. This angle is theta. So W, if I were to take moment of weight, I will take as W into 12 cos of theta. So using that, I can take this as 18 into P is equal to 100 into 12 into root 3 by 2, and you will get P as 57.73. Now, there are some other ways that you may be asked to do. So there is another sum which you may be given, and think of these sums in your own way. So take any values you want to and solve them and see how the questions are appearing. Let's say there is one ball. Okay, let's make this a bit smaller. There's one ball over here which is holding a larger ball like this. This ball has some weight, let's say 100 Newton. This ball has weight, say, let's say 200 Newton. And you're asked to find the normal reaction force A and the normal reaction force B. So question like this can appear, and you will need to solve them in the same way that I just shown you. Questions of wages, like I said, you may be given, and the easiest way to solve question of wages is by using the concept of reaction at an angle. You may be given the value of mu. So let's say mu is given to be 0.25. You need to convert into some angle tan phi and take phi as tan inverse 0.25 and solve the question in that way. If you feel uncomfortable in solving friction like this, what you can do is, let's say I'm given two blocks like this, right, which are in contact. So if I were to take the FBD of this block, so this block is prevented from moving using this block with some force, let's say P. Okay, so I will need to set some force P. I have some weight over here, normal reaction over here. Now the normal reaction always will apply parallel, sorry, not parallel. Wait, what happened? Yes, so the normal force will always apply perpendicular to this face surface. So you can take NB, let's say, over here. And since this block is prevented from sliding down this direction, the friction force will be like this, some force F, right? And with that, you can calculate the net force. Now friction, see why we are taking friction in the direction of sliding. So this block is starting to slide in this direction. So friction force on this block will be along this. So this block is applying force on this direction, since you know the forces should be balanced since the body is in equilibrium. And in this way you can solve, and of course you can take F is equal to n perpendicular cos theta, and you can solve it in that way, mu n, and you can solve it in that way. However, I do think that taking angle of tan and simply considering that if, let's say, this is the perpendicular face, if this is the perpendicular which I draw, so the reaction force should be applying R1 to this block, and if I were to consider this block, the reaction force will be applying something like this, R2. And solving it in that way, considering the angle phi, is much easier and will give you the answer in way simpler form. Okay, so let's move on to what I would say is the last topic which is there in the syllabus, that is known as belt friction. And this is something that is derived in its full form in classes. However, I will give you the easiest way of learning, that is just simply giving the formula. So let's say there is some rope like this which is tied along some ball like this. Okay, this is a very bad diagram. Let me clean it up a bit. Let's say the ball is like this. Okay, it's a perfect circle. This is in contact in all of these places, right? I'm not very good at drawing diagrams. Now here I'm applying some force T2 and here I'm applying some force T1. Basically the tensions that are being applied, right? If this angle, so the net angle where the ball is in contact, if I were to draw, this looks like a straight line. Let's just change that. Let's say here and here. Okay, just to make sure that the angle is obvious. So this angle is some angle phi, right? Then we can calculate this T1 using the value of T2 or T2 using T1, and they will be linked by the equation that is T2 is equal to T1 e to the power mu of beta. So this, okay, I wrote phi, 1 second. This is beta some angle. Okay, so beta is the total angle of belt contact, which is equal to which you will take in radians. Mu is of course the value of friction, E is of course the operator, and T2 is the first tension and T1 is the second tension. And using that you can easily calculate the value of T2 and T1. Now how can you understand which T2 and T1 is greater? This will be given in the question, or you might be given a rotating torque. So a rotating torque might be applied, and using that you can use hit and trial method. So you can either take T2 is equal to T1 e to the power mu beta, or T1 is equal to T2 e to the power mu beta, and using this you can calculate which force is larger. So whichever force is larger, opposite to that you will be given the rotating torque in order to stop the body from rotating, and you can calculate from there. So I hope I've been able to cover all of the topics in as much detail as necessary. I will also be attaching a PDF containing some important topics which I have already discussed here, but also they are given in more details from the books along with this video. And also I request everyone to solve the questions which are given from your classes so that you're able to attempt the exam much more easily. I might be releasing something else which covers the questions. We will see what I do there. So thanks for now. Best of luck for your exams. Goodbye.